All right, so number 2, they want to know what is the empirical formula of this hydrocarbon. So the first thing that we need to remember is that a hydrocarbon is just a compound that contains nothing but hydrogen and carbon, for instance CH4. But the problem is, in this case, we don't know the mole ratios, so we don't know these two numbers. If we knew the mole amounts of carbon and the mole amounts of hydrogen, we could figure that second part out. Now, you notice the information they give us here is not, they don't give us directly moles of carbon. They tell us an amount that is produced in the combustion of the hydrocarbon, and the product is carbon dioxide. But that's okay, because you remember that this is a combustion analysis problem. If we know how many moles of CO2 we have, we can easily figure out how many moles of carbon we have. And if we know how many moles of water, the other thing, we can easily find out how many moles of hydrogen we have. So that's how we're going to tackle this problem. Let's start with the CO2. Now they tell us that 1.8 liters of CO2 are produced. And so that's a volume, and clearly it was made as a gas, so you might immediately start to think about PV equals nRT, and we could solve for N. They tell us it's at standard pressure, so it would be 1 atmosphere. The volume is 1.8 liters, that's how much was made, 0.0821 and 298 for the temperature. So we could do that without doubt. But the other thing you remember is because it's at STP, it's also true that 1 mole of any gas will occupy 22.4 liters if it's at STP, and this one definitely is. So I think I'm going to go with this second approach. So 1.8 liters of CO2 is 22.4 liters per mole. And you'll notice that if I cancel those units, it will tell me how many moles I get. And I get 0.0804 moles of CO2. Now, since there's 1 mole of carbon in each CO2 molecule, there's only 1 carbon in each CO2 molecule, that will also relate to it being 0.0804 moles of carbon. So I've got this first thing I need to know. I've got X roughly, and all we got to do is do the same thing for water. Well, in water, up here, they tell us we have 2.16 grams of water that were made. Well, that's pretty easy to convert that to moles. I'm just going to do 2.16 grams, do the molar mass, and voila, I get 0.1199 moles of water. Now, that is not going to be 0.1199 moles of hydrogen, because there are actually 2 hydrogens in each water, so I need to do that mole ratio. Alright, and there we go. So there are 1 mole of water for every 2 moles of H, because there's 2 H's per water, and when I do that I get 0.2398 moles of H. So now I know my mole amounts of C and H, so I know X and Y. But of course we have to have them in whole number ratios. So which of these two do you think we're going to divide by to get them to a whole number ratio? Well, the answer is always the smaller one. So I'm going to divide this one by 0.0804, and that's going to be 1. I just got to figure out this divided by 0.0804, and when I do that, I get almost exactly 3 for that answer. And I didn't write down that last step, but you definitely should. Divide this by 0.0804, and you'll find out that the ratio is C1H3. So that is the empirical formula, and that is part A. Now, if you have a very good memory, you might expect that now that we know that the empirical formula of this stuff is CH3, that the next thing to do would be to figure out the molecular formula if we know the molar mass. So if we know the molar mass, we could determine if it's this or C2H6 or whatever. And that's coming up, but it's not part B, it's part C. You can see it down here. What is the molecular formula? So whatever's going to go on down here in part C is probably going to be to figure out the molar mass. And it looks like they're using gas laws. But we'll get to that. Let's look at B. What is the mass of the hydrocarbon consumed? And this is it's a very unusual question. But you remember that we knew the number of moles of carbon that were made in the CO2, and we knew the number of moles of hydrogen that were in the water that were made, and they had to come from somewhere, and they had to come from this particular hydrocarbon. So it's an unusual question, but let's go with it. So I don't have the exact numbers from the previous slide at the moment, but the carbon was somewhere around 0.240 moles, and we found out that the hydrogen had about, I want to say 0.0804, somewhere in there. Oop, going the wrong direction there. Let's erase some stuff here and get it right. So now that we remember those amounts, then it's simply a matter of finding out how many grams each one of these corresponds to, and all of that must have come from the CH3, and so that we're just going to add them up and get the total grams. Alright, now I was about to do this and I noticed I got my labels backwards. The top one isn't carbon, that's the amount of hydrogen we had, so let me write over that. This is the amount of hydrogen we had, and this is the amount of carbon. It really matters because I don't want to use the wrong molar mass in the wrong place. So if I multiply this times the molar mass, 1.01 grams per mole, so we're essentially just converting our mole amounts back to grams. And this one is 12 grams per mole. Then I'm going to get about 0.242 grams of hydrogen and 0.961 grams of carbon, and then that must mean that we had, if I add them up, 1.203 grams total for our CH3 up here. So there's B. I forgot to check for sig figs. So it's all the information's coming from up above and from the previous step, and those had 3 sig figs in it, so we probably should do 3 sig figs here. So I'm going to say 1.20. Now on to part C. This is what we were expecting, I think, more than what was in part B. They just want to know what the molecular formula is if the empirical formula is CH3. And so remember, if we know the molar mass, it should be pretty straightforward. Well, they're giving us gas information here. They tell us it's in a 1 liter container, they tell us the temperature, they tell us the pressure. It's looking an awful lot like, well, how do we get the molar mass from PivNert? Because that's a lot of PivNert type information. And you'll notice that molar mass is always in units of grams per mole. We saw that on the multiple choice homework. So if we knew the grams of the stuff, which we just figured out in the previous step to be 1.203 grams, then all we got to do is figure out the moles to put on bottom. Well, if PV equals nRT, we can find the moles from that. So I did the rearrangement here, and I went to plug in some values. Nicely up here, 760 millimeters of mercury is exactly 1 atmosphere. And then I added 273 plus the 32 to get my temperature, put those in the appropriate places, used 0.0821, and came out with 0.07188 for our amount of moles. So we can go ahead and put that in our molar mass calculation, 0.07188. Alright, so I'm looking at the key and I clearly made a mistake. Hopefully you guys caught it. It's not 1.8 liters. It was originally, but they're telling us the closed vessel is 1 liter. So that means that this is really 0.040 moles. And if that's 0.040 moles, we come out with 30.1 grams per mole. And since our empirical formula was CH3, and that's 12, 13, 14, 15, that's 15 grams per mole, then I would say clearly 30 divided by 15 is 2, so our formula really should be C2H6. And lastly, part D, almost pretty easy compared to the other ones. We get C2H6. We decided was our molecular formula. It was doing a combustion with oxygen, and we're going to get CO2 and water. Notice they didn't say net ionic equation or anything, just the balanced equation, but it wouldn't make a difference because they're all covalent, so it'd all be the same. Usually we do carbons first, so I'm going to say this side on the right needs 2 carbons, and then we do the hydrogens. There's 6 on the left, so I'm going to put a 3 there. And then we've got to do oxygens. There are 4 right here, and another 3 there, and of course that means there's 7, which is an odd number, so we'd be tempted to put 3.5 in there where the oxygen goes. Well, let's go ahead and do that because we can always do it in a different color. Let me erase this other stuff. And then all we've got to do to get whole numbers is double everything. So it's going to be 2, that's going to be 7, that's going to be 4, and that's going to be 6.